So, hello friends, very good morning to all of you. Here I have decided to talk about a very important semiconductor two-terminal device which is known as tunnel diode or Esaki diode after its inventor Leo Esaki in the year 1958. So here I have shown the symbol of a tunnel diode. There is a slight difference between the symbols of PN junction diode and a tunnel diode. This is the change you can observe, which is the difference between the two symbols. Anode and cathode are the two terminals. Now this tunnel diode is actually made of the semiconductor materials which are degenerately doped or heavily doped. So the PN junction in this device is a heavily doped PN junction, and because of that heavy doping, the depletion region is very thin, of the order of 10 nanometers in width, and because of this very thin depletion region, an extremely high electric field exists within the depletion region, and as a result the conditions are favorable for the quantum mechanical tunneling of electrons from the one side of the junction to the other side of the junction. So the applications of this device because of quantum mechanical tunneling can be in case of high speed switches as well as in case of microwave circuits. So let us begin with by asking three questions to ourselves, and these questions are basically: how does tunneling lead to the ultra fast switching action of device? The second question we may ask is, why does the tunnel diode show negative resistance? And the last is why is it especially useful in microwave applications? So during this lecture we will try to find out the answers to these questions. For the materials to be used for the construction of this device, here I have listed three materials: gallium arsenide, germanium and gallium antimonide, in the order of preference of their use for the construction of this device. So gallium arsenide has some important features in its favor. The first feature is its highest value of peak to valley current ratio for different materials, and gallium arsenide has the highest value for the peak to valley current ratio, which is known as PVCR also, and which is a figure of merit of this device. So because of this higher value, gallium arsenide is preferred, and secondly it has also a higher peak voltage which lies in the range 200 to 500 millivolts. So because of these things, this gallium arsenide tunnel diode is utilized in faster switching applications, as well as it is also preferred for microwave applications. Now another material suitable for the construction of a tunnel diode is germanium, because it is easier to control doping in case of germanium tunnel diode, and also it has a significantly high peak to valley current ratio. So these two factors goes in favor of germanium for its use to construct a tunnel diode, and the peak voltage for this germanium tunnel diode is slightly lower than the value for gallium arsenide. The third material is gallium antimonide, GaSB, which is used when low peak voltage, low power design is the requirement. Now to our surprise, silicon, which is the most important and most favored material for the construction of ordinary PN junction diode, is not suitable for the construction of a tunnel diode because it has a low value of peak to valley current ratio. So because of that, silicon is not used for the construction of tunnel diode. So here we can see that construction for this tunnel diode has certain features. This PN junction is basically degenerately doped, means very high doping levels in the P region as well as in the N region. So semiconductors are therefore termed as degenerate P type and degenerate N type. Impurity level reaches up to 10 raised to the power 19 to 10 raised to the power 24 atoms per cc of the semiconductor material, and this level is around 1000 times that of an ordinary PN diode. So then the width of the depletion region is very small, of the order of 10 nanometer, which is again 100 to 1000 times smaller than that of ordinary PN junction diode. And another feature is the existence of extremely high electric field within the depletion region, which reaches up to the level of 10 raised to the power 8 volts per meter. So these three things combinedly favors the tunneling of electrons from one side of the junction to the other side of the junction quantum mechanically, even if the electrons do not possess the sufficient energy to overcome the potential barrier existing at the junction. So to understand the whole characteristics of this device, we will divide it into 5 parts. The application of external bias under the zero bias condition, that is no bias, or the equilibrium condition, in which condition the Fermi levels are at the same level throughout the device. Then in the second case we will apply a small reverse bias and we will see what happens to the flow of current through the device. And in the next case we will see that what is the effect of applying a small forward bias between the values 0 and the peak voltage. And after that we will increase forward bias and we will see that what is happening after the forward voltage has exceeded the peak voltage of the tunnel diode. And finally we will see that what happens when the voltage has even increased the valley voltage. So here I have shown the energy band diagram for this tunnel diode, and the tunneling can take place from filled state to an empty state if the states are overlapping on the energy scale. So in the zero bias case, that is in the case A, we can see that these filled states are overlapping with these filled states on the P side and just below the Fermi level. In case of this degenerate semiconductors, Fermi levels lies within the conduction band or within the valence band. So this dotted line is throughout at the same level, and this is for the degenerate P type and this is for the degenerate N type. So up to the Fermi level these states are filled with electrons, and here these states are filled with holes. So these filled electron states are now overlapping the filled electron states on P side. So there is no net tunneling between these states, and these empty states are overlapping with the empty states in the N side. So no net tunneling means no current flowing through the device. So this is represented by this point. In the second case I have shown in this case a small reverse bias is applied, and that reverse bias causes the electron energies on the N side to decrease, so the bands shift downwards, and in this case this makes the filled valence band states on P side to overlap with the empty states on the N side conduction band. So the electron tunneling is shown from P side to N side, and this tunneling is significant at small reverse bias values. So because of that, we will observe that a sharp increase in reverse current is seen as we increase the reverse bias in small steps. Then in the small forward bias case, we will see that electron energies on the n side will increase, so the bands will shift upwards, and here we can see that these conduction band filled states lying between ECN and EFN are now overlapping with these empty states between EVP and EFP. So as we go on increasing the forward bias, we will see that more and more number of filled states are overlapping with empty states on the P side. So quantum mechanical tunneling with increase in proportional to the small forward bias. So current will sharply increase and will become maximum at a particular voltage, which is known as the peak voltage in this case. And what happens? So the current has reached up to this level when the applied forward bias is at the value Vp. Now after this Vp value, that is if we increase the forward bias beyond this Vp value, then we will see that the bands will start bypassing each other, and filled and empty states will also be bypassing each other. So less number of filled states will now be facing the less number of empty states. So the tunneling will start decreasing, and this will continue up to a value of forward bias, which is known as valley voltage or VB. So between BP and VB, we will observe a decrease in the forward current with increase in the forward voltage. So this is the important reason of the IV characteristics of a tunnel diode, in which the diode is showing a negative differential resistance, or you can see that diode is producing power rather it is consuming power. So this is an important feature of the characteristics of a tunnel diode, which is utilized in the diode's application as an amplifier or as an oscillator. Now from this 0 to VV value, diffusion current is very small, but the current is mostly because of the quantum mechanical tunneling. But after this value, the forward bias has increased to a sufficient level, and the whole current is now mainly due to the diffusion effect, and tunneling current is present, but that is very small compared to this diffusion current. So after this value, the diffusion current takes over the tunneling current, and the tunnel diode operation is just like an ordinary PN junction diode operation in this region. So this graph shows the whole characteristic of the tunnel diode. Now here I have shown the equivalent circuit of a tunnel diode, which consists of the negative resistance, which is between the peak point and the valley point of the characteristics of tunnel diode, and in parallel with that we have the diffusion capacitance, which is basically the capacitance of diode that dominates when the diode is under forward bias. So this parallel combination is in series with two other components, is lead inductance L, which is due to the package and lead wire inductance, and a small series resistance of the order of 5 ohms, which is actually the ohmic resistance of the semiconductor material, and also due to the metallic leads. So these are the components which will decide the high frequency applications of tunnel diode. Now here I have listed some of the important features of tunnel diode. A figure of merit of tunnel diode, which is also known as PVCR, is actually the ratio of its peak current to the valley current, and if this ratio is high, then diode is considered as a good diode, and overall device performance is judged on the basis of this figure of merit of the tunnel diode. Now, because the quantum mechanical tunneling takes place at the speed of light nearly, so the process is almost instantaneous, and because of that the diode is suitable to be used as a ultra fast switch. And the ultra fast this quantum mechanical tunneling again occurring at the speed of light means the noise level in this device will also be very low. The frequency range in which the tunnel diode oscillator can be used lies in the range 1 gigahertz to 200 gigahertz, and this can this can extend well into the microwave range. Here, to sum up these things, the diode shows a negative differential resistance in the characteristics between its peak point and valley point. It is extremely fast switch like operation, or because its on off switching time can be in the order of picosecond to low nanosecond range. And then, since there is no minority carrier storage delay involved, so its high frequency response is quite good. Tunneling taking place at the speed of light, so noise level is also very small, and this device is also stable for its operation against temperature variations and the existence of radiation. Here again I have listed some of the applications. Tunnel diode can be used in microwave oscillators, in relaxation oscillators, that means non-sinusoidal oscillators, to generate non-sinusoidal waves like square waves, triangular waves, and etc. other waves shapes. High speed switching, ultra fast logic and pulse circuits may be this can be used. Then low power microwave amplifiers, frequency mixers or frequency converters. And finally, because you can see that from its characteristics, a single value of current corresponds to 3 different values of voltages, so it is having just like a feature of memory. So this device is also suitable to be used in fast memory and storage circuits. So basically this device is very important device, and its inventor was given a Nobel Prize for its invention. And to sum up, it is a two-terminal semiconductor device with heavily doped semiconductors used for its construction, and leading to a ultra thin depletion region in which an extremely high electric field exists, and it gives rise to high speed operation, high speed switching operation and microwave circuit operations. So this is all about from my side about tunnel diode. Thank you, and we will see some other device in the next lecture. Till then, bye bye. Thank you.